In this video we'll be learning about Hamilton cycles, in particular what they are, and also how we might approach finding these in a graph. So first things first, a Hamilton cycle's definition is right here. A Hamilton cycle in a graph G is a cycle, and it must contain all the vertices in the graph G that it lies within. So let's look at a couple of examples. This example on the left would be our graph G. This is the starting graph, and we're looking for a cycle in this graph. So we want the cycle to contain all 6 vertices. That's the goal. And so our first question is, does this graph have a Hamilton cycle? It's a yes or no question. And then furthermore, if it has one, we would want to exhibit one, actually find such a cycle. And so this graph G happens to have a Hamilton cycle. And here's one. We could start at this vertex 1, and we could go to 4, to 5, to 6, to 3, to 2, and then back to 1. So it is a cycle, because we can walk around the edges that we chose and end up back where we started. And it's a Hamilton cycle because all 6 vertices are contained within this cycle. So I don't have to pick all the edges. I just have to pick edges that form a cycle as long as I contain all the vertices. So our answer here would be yes, and the notation for this cycle would be 1, 4, 5, 6, 3, 2, and then when I put those in parentheses, that implies that this edge 2 to 1 is also in there. So this is the cycle that contains the edges 1, 4, 4, 5, 5, 6, 6, 3, 3, 2, and 2, 1. So that's a Hamilton cycle in that graph. This graph on the right, I would claim, does not have a Hamilton cycle. And it's a little harder to argue that it doesn't have a Hamilton cycle because you would have to just somehow show that there's no way it could possibly have one. But this graph possesses a vertex of degree 1, and this ends up being the reason that this particular graph has no Hamilton cycle. Because if you think about it, any cycle that contains 4 is going to have to use 2 edges at 4 because it's going to have to arrive at 4 and then leave. And so the fact that no even cycle can contain vertex 4 means that no cycle can contain all the vertices. So that one's a no, no Hamilton cycle. So let's move on to thinking about how we might find Hamilton cycles in a graph. So we're interested in some kind of algorithmic approach. If we're given a graph G, like this one here, this 5 vertex graph, how would we find a Hamilton cycle? And so one approach, which we call the brute force approach, or brute force algorithm, is to exhaustively list all possible cycles and then check if they are or if they're not, and eventually we'll find one if one exists. So this is just list all possibilities until you find one. And for this, we don't just randomly choose vertices or cycles, although we could do that, but we kind of systematically go through them. So the first obvious choice for a possible Hamilton cycle would be this one, 1, 2, 3, 4, 5. So I list these out, and then I check if these edges are indeed in the graph. The edge 1, 2, 2, 3, 3, 4, 4, 5, and then 5, 1. So I check 1, 2, it's there, 2, 3 is there, 3, 4 is not there. So that's not a Hamilton cycle in this graph, but it doesn't mean it doesn't have one. I just move on to the next possibility. And so somehow I need to switch these at the end, and this seems like an obvious next choice. You just switch as few as you need to. So I'll go check these. So 1, 2, 2, 3, those are good. 3, 5, that's there. 5, 4, that's there, and then 4 back to 1. So actually all these edges are there, so that is a Hamilton cycle. It's this one. 1, 2, 2, 3, 3, 5, 5, 4, 4 back to 1. So it just happened to be that I found one on the second iteration, but I may have had to have run through a bunch of possibilities. So this returns a yes, and it returns the actual cycle. And if a graph has a Hamilton cycle, the brute force approach will find it. If it doesn't have a Hamilton cycle, the brute force approach will be a comprehensive argument that it doesn't, because it lists all possibilities, and if they're all a no, then there's no Hamilton cycle. So we might notice that the number of number of 5 tuples this would have to look through would be 5 factorial. And we can use our known counting techniques to figure out that if you're listing 1, 2, 3, 4, 5, and the order matters and you can't repeat, there are 5 factorial ways to order those numbers, 1 through 5. So that's 120 in this case. Which means that theoretically, in the worst case scenario, I would have to go through all 120 of these different permutations and check if they're a Hamilton cycle or not. I just got lucky and found one on the second one. So in general, if you have n vertices, this algorithm will have to check n factorial different permutations, listings, orderings of the vertices. And this is a lot. So this would actually take too long. In theory, if n is big, this algorithm won't stop running because there are just too many possibilities. So while the brute force approach to finding Hamilton cycles is comprehensive, it'll definitely give us a yes or a no. Sometimes it's too slow if we have too many vertices. So it works, but we would like to find more efficient methods for faster ways of finding Hamilton cycles. And in the next couple of videos, we'll examine ways in which we can do that, different algorithms.